Hey everyone, thanks for listening. My name is Anirban. I'm a postdoc at SLAC. I'm going to talk about direct detection of dark asteroids. This is a work that I did with my collaborators, Sebastian, Philip, and Kevin at SLAC. What are these dark asteroids? These are basically macroscopic dark matter objects which can form in varieties of dark matter models. For example, I'm giving here three model examples. In some dark asymmetric dark matter model, there could be dark nucleosynthesis, very similar to what happens in the visible sector during Big Bang nucleosynthesis. Basically, fundamental particles in the dark sector forming composite objects, and they can further collapse and form bigger objects. Also, in models with dark QED, where there is a light mediator, which mediates a long-range force between dark sector particles, there is an efficient channel of cooling. So a dark matter halo can collapse under gravity through this cooling process and can form macroscopic objects. And also in another model, like in dark QCD, where there is a first order phase transition from a universe where the fundamental degrees of freedom are dark quarks to another phase where the quarks form baryons. And in that case also, it's possible that these some pockets in the universe could collapse and form dark matter nuggets. So in these kinds of models, it's possible to have macroscopic compact dark matter objects, and these are the things which I'll be calling as dark asteroids. Now, this plot here gives an idea of what is a parameter space in which we will be interested. So you can see that the mass of these objects could be anywhere between 10 to the minus 18 to 10 to the minus 11 solar mass, and various possible radius. Now, there are certain constraints that are existing in this parameter space. So in this high mass end, we have microlensing constraint coming from the hyper supreme camera from the Subaru telescope through the observation of the Andromeda galaxy. And in this high radius end, we have constraints coming from the CMB and heating of gas cloud when if you have strong interactions between dark matter and baryons. You can heat the gas cloud, or you can change the CMB anisotropies, and non-observation of any of those things put constraints or upper limits on this parameter space. Now, the main issue with this type of dark matter objects is that they're very rare. The number density of these objects is very small. So here I'm showing two blue lines to show that the encounter rate of these objects, if you take the whole Earth as a single detector. So you see that for a mass of 10 to the minus 15 solar mass, there's only one event in 10 to the 10 years. Or even if you go to much smaller mass of 10 to the minus 18, the encounter rate is like just only 1 in 10 to the 7 years. So these are, it's not possible to do any terrestrial experiment to constrain this type of models. So one has to look for a bigger detectors like a star. So here is where the analogy with our conventional direct detection experiments in the dark matter physics comes in, where we have a detector volume where a dark matter particle comes in and hits an atom in the detector that gives out some radiation which we detect with our detectors. Very similarly, what we are considering is we are considering all the stars in the Milky Way or within a certain region of the Milky Way as the detector. So when one of these dark asteroids comes and hits the star, that will create some emission which we'll detect with our telescopes at Earth. Now let's see how these things will work. Let's take the example of the sun, where dark asteroid comes and collides and it penetrates through the surface. Now, if you look at the typical speed of this collision, which is, it would be for sun, it is say more than 650 kilometers per second. But if you look at the speed of sound near the surface of the sun, that's very small. That's only a few kilometers per second. So the collision would be hypersonic, and that would create a shock wave in the medium. And for these high velocities, we are assuming that this shock wave is created. I mean, this shock wave can be approximated as a blast wave, very close to the trajectory of this dark asteroid. And this scenario is very similar to what happens when a meteor passes through the atmosphere. So we have this tube of blast wave coming out from the trajectory of the dark asteroid. Now, after a distance of which is typically determined by the size of this dark asteroid times the Mach number, beyond that distance, that shock quickly becomes weak, and it remains weak for most of its propagation through the interior of the sun. So as you can see in this figure, these blue contours are the wave fronts. So they come out, and because of the change in the speed of sound in the interior, which increases towards the center. So as a result of that change, these wave fronts comes out and bend towards the surface. And that helps to channel the energy of the collision towards the surface. Now this shock remains weak all until it reaches very close to the surface, where it gets strong again because of the sudden drop in density. So what we do is we use the standard weak shock theory to calculate how much energy is remaining in that shock wave. And when it reaches a point, a layer below the surface, which is in good thermal contact, we say that this whole outer layer is heated to some temperature TAF, and that gives out the radiation. And that also sets the emission waveband, in which part of the electromagnetic spectrum the emission will be in. So for example, for the sun, for sun-like stars, the emission would be mostly in UV, and that would be followed by in the emission in the visible range. But at the beginning, we also expect a prompt emission of X-ray from the region where the collision first happened. So here, this shows a cartoon of the light curve that we can expect from such a collision. Disclaimer that we did not do any detailed hydrodynamic simulation of this event. This is only based on analytical estimate and using a standard weak standard shockwave theory. But we expect that there will be a initial sudden burst of X-ray, which would be followed by a longer UV emission and an optical emission from the star, and that's for the typical sun-like stars. This contour plot shows the energy emitted from such a collision. As you can see, the emission energy varies a lot depending on from where in the parameter space you are, starting from 10 to the 29 or to even above 10 to the 37 erg. So generally the energy increases if you go towards higher radius or higher mass, and that's pretty understandable. And additionally, what is happening is that the energy is saturating in both directions, both in large mass and large radius. And that's because when the radius is very large, the object, this dark asteroid, does not penetrate much inside the sun, much inside the star, because of the drag force is too high, and in that case, all of the collision energy is coming out. And for very large mass, the dark asteroid just punches through the whole star and it comes out from the other side. So in that case also, there is only a limited amount of energy that's deposited inside the star. Now, to observe this kind of things, what we have to do, or we are proposing to do, is a transient search. For this kind of search, we have to keep three things in our mind. One, that we have to observe as many stars at a time as possible. Second, we have to distinguish them from stellar flares, because they might look like very similar. I mean, the light curve of these events might look like very similar to a flare event. And also, we have to look at a dark matter dense region where there is a lot of dark matter, where we expect to have a lot of dark matter. Now, for that, we are proposing two kinds of search that can be done. First one is to look for these kind of things in a local neighborhood of the solar system. We picked out two telescopes that can be used. One is this ultrasat which is a UV transient telescope being planned by the Israeli Space Agency, and we could also use LSST, which will be done by the Vera Rubin Observatory. And these are ideal for UV search. That's for the K dwarfs or sun-like stars, and they are good candidates for targets because of their large mass. But we can also use the red dwarfs or M dwarfs. The advantage is that they are more abundant in our neighborhood, but the problem with them is that they also show more flare activity. So for the same energy, you might not be able to distinguish between such a collision and a flare. Also, red giants will be another good candidate because of their large size. So they're like 100 times smaller, 100 times bigger than the sun. So the encounter rate is much higher, but the energy that will come out of these red giants is much smaller, because they are bigger, they are more fluffy, and most of the energy is getting lost while the shock wave propagates in the interior. Another way is to look for, do a focus search, and the best place would be a globular star cluster in our Milky Way. We already know about the existence of like more than 160 globular clusters only within our Milky Way itself. We have picked out this particular globular cluster called 47 Tucanae. These are basically star clusters, but there are millions of stars within a radius of only several parsec. So they are very dense objects with lots of stars. This particular cluster is relatively close to us, about a distance of 4.5 kiloparsec. It's also away from the galactic center, which is good. And there is very little UV dust extinction in that direction. And finally, also that the Hubble Space Telescope has already observed this particular cluster for a long time. So there is already data available for this cluster. Now, this is what the exclusion regions will look like if we can do this kind of searches. So in this purple contour is for the search in the local neighborhood on the K dwarfs using the Ultrasat satellite telescope. This is probing the lower mass region because of the lower density of stars. And this blue contour is by a search of 47 Tucanae by the Hubble telescope. And this can go to a very large mass because of the, as I said, the stellar density and also dark matter density is expected to be much higher in a globular cluster compared to our local neighborhood. So this type of search will probe a much higher mass end of dark matter. So, and in this, so at this higher mass end, these contours are limited by the rate. I mean, here, as you go towards even a higher mass, the rates become even smaller. And in this lower radius part, it is limited by the flare rate, where the flare frequency becomes comparable to the frequency of collisions. And in this part, the contour is limited by the sensitivity of the telescope, where the event or the event becomes too dim to be observed by the telescope. So what are the future outlooks? As I already have said that the Hubble Space Telescope has already observed this particular globular cluster, 47 Tucanae, for a long time. So the data is already should be available, and one can in fact go and dig out that and put some constraint. One can also look for other globular clusters which might have black holes at the center, which will tend to increase the dark matter density, which will again enhance the chances of collision. Another good candidate would be brown dwarfs, which are supposed to be more abundant than even any other stars, even more than red dwarfs. But the problem is that we haven't observed many brown dwarfs so far, so we don't know where they are. But in future, maybe that could be, brown dwarfs could be used as a good target. And of course, another way forward is to do a detailed hydrodynamic simulation of this shock propagation and cooling, which would give us a very realistic idea of what the light curve would look like. And in fact, if we have that knowledge, then we can even distinguish between such a collision and a flare of equal energy. And we can even maybe use that to reject the flare background. Finally, we can also use the galactic center because that has a very high dark matter density. It also has a supermassive black hole at the center. But the problem is that it has a very large foreground and lots of dust around it. And so it's probably right now, it's not the best place to look for such events. And I'll stop here. Thanks for listening again. And if you have any questions, I'll be happy to answer during the live session. Thank you.